Welcome to UVU CS3060 Lecture 5.2, where we talk about the shortest job first scheduler. So when we talked about the first come first serve scheduler in the previous the previous lecture, we discussed how there was a problem with the scheduler when there was particularly long jobs that preceded some particularly short jobs, and we called this the convoy effect. So in the shortest job first scheduling, what we do is we associate with each process the length of its next CPU burst, and we decide which process is going to execute based on that length. So a decision is made based on the process length or the burst length for a particular process, and the shortest ones will actually be scheduled first. So the shortest job first schedule is optimal, gives the minimal average waiting time for a given set of processes, meaning that if you have a list of processes, it's always going to give you the least waiting time for all the processes. And especially in a non-preemptive system, which shortest job first is a non-preemptive system. So let's go ahead and mark that up. So this is a non-preemptive scheduler, meaning that the scheduler lets each job run to its completion. Each CPU burst can run to its completion. But we have a couple of problems. We really don't know how long that burst length is going to happen. There's no way really to predict with 100% accuracy what that burst is going to do, especially when we're working with logic that can be conditional or loops that depend on the number of iterations. We could ask the user, and sometimes the program could provide a length of time, but this is unreasonable, especially when you have processes that are moving very quickly. So here's an example of a shortest job first. Here we have a queue. It has processes 1, 2, 3, and 4. This is their submission order. And this is their burst time, 6, 8, 7, and 3. Now, what the shortest job first does is it looks to see which one is shortest. So it starts with process 4 here. And it schedules process 4. Process 4 is able to run to time 3, and then it is taken off of the queue. Now process 1, the next process that's selected is the shortest job, which is process 6 here. It runs to time 9, and process 1 is removed from the list. Now it looks at this list, which one is shortest? Process 3 is shortest, and so it runs from 9, and we'll erase this, to 16. And it is removed from the list. And then finally, we have process 2. Process 2 runs from 8. It runs for 8 milliseconds, which means it runs from 16 to 24. So if we take the average wait times for these, we wait, process 4 waits for 0, process 1 waits for 3, process 3 waits for 9, and process 2 waits for 16. Add those together and divide it by 4. Here is our average wait, which is also the same as our response time in this particular algorithm. So this is the optimal. It is actually it can't get any better when it comes to wait times. You cannot get anything shorter. It is provable. So this is certainly an improvement. We've eliminated the convoy effect. So we don't have any convoy effect with shortest job first. We've eliminated it entirely. but we still have this lingering doubt about how do we figure out what the process burst times are going to be. What is that number? Well, what we do is we use an algorithm to determine the next burst time based on a few values, okay? We call this exponential averaging. So we're about to introduce you to a concept called exponential averaging. Exponential averaging allows us to estimate what the burst time is going to be for a particular process. So at a particular time, we'll call this at time n plus 1, so we're about to execute a new process. At time n plus 1, what we do is we take a look at the last burst time, t of n. This is the last burst time for that particular process. And then we also take a look at the average from the last particular burst, or the actual last predicted value. So if the last predicted value was particularly low, that usually indicates that there were a lot of short bursts. But if the previous time that actually executed was very long, that is kind of an aberration from what was actually predicted last time. Now there's this value called alpha. This alpha value determines whether or not how to balance the prediction based on the last burst time versus the last average time. So let's say, for example, we had at t sub n, so the last actual burst time was 24, meaning that it took a little bit of time, whereas tau n was actually 3, meaning that there were lots of very short burst times. Well, and let's say we set alpha to 1/2. What's going to happen is it's going to take half of this value, so it's so t or tau of n plus 1 is going to be 24 times 1/2. Plus 1 minus 1/2, which is, again, 1/2. It's going to be tau of n times 1/2. Well, 1/2 of 24 is 12. 1/2 of 3 is 1.5. And so 13.5 is our guess for tau n plus 1. And this is actually a fairly reasonable guess depending on the last value that we received. And whenever it comes to tau n plus 2, it's going to take that guess and whatever the previous actual burst time was. And so this will go up and down depending on how the burst times go. This exponential averaging allows us to predict how long a particular job CPU burst might be, and then allows us to choose the proper scheduling for that time. Now remember that shortest job first is a non-preemptive algorithm. We will now talk about the next algorithm called shortest remaining time first, which is a preemptive version of shortest job first. Now, you can see here this is an example of exponential averaging and the prediction of the next burst. The black line here actually shows the actual bursts. You'll notice here that it starts at 10 predicting at 10, but these short bursts here cause the exponential average to go down. Until at this particular time, we have a burst, it goes into a high burst, at which point the exponential average starts climbing up again to match this long length of time where there are many long bursts for this particular job. So you can see that exponential average is a nice smooth curve compared to the rather jagged burst curve, but it does fairly closely predict how that curve will look. So again, some examples of exponential average. If our alpha is 0, then it really doesn't consider recent history. Recent history doesn't even enter into it, and all it's doing is using the previous guess every single time. So with alpha 0, it never really adjusts. If alpha is set to 1, we actually only consider the CPU burst count. And so the nice smooth curve that we saw in the previous diagram actually matches the jagged representation of the job links, and thus does not give an accurate view of how the process has operated in the past. And we can see what happens when we expand this particular formula. It actually you can show the recursive nature of this, and that it should go back to the very beginning where when the process first started, and it will give a full view of the history of that particular process. So because alpha and 1 minus alpha are less than or equal to 1, each term has less weight than its predecessor. This ends UVU lecture CS3060 lecture 5.2, where we talk about the shortest job first scheduler.